So let us have the implementation on the Quartus tool. Yes, so we can open the Quartus tool and it will be observed as a graphical user interface of the Quartus tool like this. So once you go with once you see this one, we have to go with a new project. We have to create a new project, and for every file we have to create a new project here, and it will be stored somewhere in the Quartus file, right? We need to give that name of the project. And one thing as a precaution that we have to take it, whatever that project name you give it, the same name should be there for the module name also. So if JK FF1 is the name I'm trying to prefer, and JK FF30, let's suppose 30 I'm trying to prefer, in the sense that is the project name, we have to use the same name for the module name also. Give next. Yes, give next. Give next. We are not any implementation, we are not doing it for any FPGA, so we need not to bother about the rest of the changes across this step. Just give next, that's it. Give next and finish. So we could create a project, and what we do is just create a file, new file, Verilog HDL file, give OK, and there like we have to write the program. So once again we'll write a program over here. Module name is, I told that JK flip flop is the name, JK FF 30, just to prefer the same name, and J comma K comma clock comma RST comma and Q comma QB. These are the outputs, right? These are the ports, module name, module ports, and declaring these ports are like input ports, right? Input ports, and output register Q comma QB. So these ports are declared as output ports, where I have a net data type also. Yes, present state and next state, these two are declared as a net data type. So register present state comma next state, and make sure the present state and next state what I am keeping a bucket, it should be accommodated with the states which I am trying to assign. If states are assigned with the one bit variable, if states are assigned with one bit variable, we can keep it as it is, but if it is 2-bit variable, I have to increase the size of the register where it 1 down to 0, so it should be a 2-bit data. After that we should concentrate on assigning a parameters over here. Parameter S0 should be with the 2 tick of B00. So tile is the symbol that I am assigning for the S0. So when there is a tile, first team should be selected. Tile head, second team, third team head tile, fourth team head. But we don't have that money. We just have two teams, S0 and S1. So S0, S1 will be again 2 tick B01. Right. So parameter assignments also done, state assignments also done. Now we go with the individual modules. We just go with the procedural statements. Always at the rate begin end. This is the one procedure block, and what I am trying to do is I will be using three procedure blocks. One is for the memory one, and another one is combination circuit one, another one is for combination circuit 2. So I will be using command lines over here. So here I am defining memory, here I am defining C2 combination circuit 2. So here I am defining C1. So while I am defining this one, the memory circuit, we should know what is the combination of the inputs that I have to mention in the sensitive list. When I have a positive edge of clock, I need not to mention any kind of NS here. NS and clock and reset, these are the three inputs. Actually, I have to add all three inputs in the sensitive list, but I have only priority with the clock. When the clock pulse is coming, then only the next state will be loaded into the present state. The count should be incremented upon the clock, as we know. In the same way, when there is a clock, then only the states need to be changed. So that's why what I do is pause edge clock itself used over here in the sense list. So here that begin statement, right? I will be using one condition over here. If that it depends upon the reset RST, when there is a reset is activated. So this is the bucket where present state is the called the bucket name is present state. It should be loaded with S0 irrespective of the state it should come to the S0. If it is there in the S1 also, it should come to the S0, means presently it will be there in the S0. Present state should be it comes to the S0, right? Else it can go to the any state. Whatever the next state it generated, the present state go to the next state. So PS equal to NS. And one thing we have to remember clearly, so if it is the memory module definition, when we have it, the present state is the output. So here the data is coming like this is what the output means. When we are declaring the statements, every statement should be like a present state equal to what, right? So here also present state equal to what, and here also present state equal to what. So this is what your module definition for the memory. So in the same way we'll do the module definition for the C2 circuit. So here the C2 circuit, and you can understand this one is output over here, it is next state. Yes, so here output is present state. So all the statements should be ns equal to what, all the statements over here should be what is the present state. So here always at the rate, always at the rate, if it is the next state, the present state value is required and the inputs also required. Based on the inputs and present state, it will be generating a next state. If the JK flip flop is at a 0 state, if the combination of 0 0 is given and 0 1 is given, 1 0 is given, 1 1 is given, based on that information it will move to the S1 to the any state. Next state will be predicted based on the present state as well as inputs. So that's why what I do is I'll be taking present state as a one combination, one input, and a j comma k, these two also one, these two also added in the sensitive list. Means this combination circuit will be doing process upon any one of the input change, either j change or k change or present state change. The next state should be responsible to generate a next state. So how it is generating a next state is, if it is there in the S0 or S1, based on the case present state, based on the present state case, right? Either it is in a S0 or S1. If it is in the S0, what happening is begin if what is if, so you can see it here. We can see it here. Now we are assuming that the particular flip flop is in S0 state. That will be the case, right? S0 is the case. Now when it is in the S0, it can move to the S1 based on these combinations, right? I will be writing that combinations, the j equal to 1 tick b 1 and k equal to 1 tick b 0. This is one combination, right? Or this is the another combination, j equal to 1 and k equal to 1, j equal to 1 and k equal to 1. For these two combinations, we are expecting that right, for this condition. For this condition, what is the statement we are expecting? As that ns is the statement, ns should be what is ns? So ns next state should be, it should go to the s1, so ns equal to 1 s1, right? This is one condition and statement. And the alternative for this one is else, when else, right? When else, otherwise these two conditions or combinations are not given, it will be the rest of the combinations will be a possible combinations. So then that next state should be s1, next state should be sorry s0. Yes, this is how I declare my output combinations for the state s0. Yes, so when that in the s1, when it is in the s1, when it is in the s1, right? When it is in the s1, so now we assume that the state is s1, so there will be possibilities it will go to the s0, it will be going to the s0 for the given combinations 0 1 and 1 1, 0 1 and 1 1. So j equal to 1 tick 0, that will be the one possibility, 0 1 0 1 possible, sorry 0 1 possible, 0 1 possibility, or 1 1 possibility, 1 1 possibility. Under these two conditions, any one of the condition, that next state will be s0, it will come to the s0, otherwise it will be there in the same state s1. Yes, so right. So now coming to the last state, like I will be going with the end case. I have to end the case every time, so end case, right? End case. And when it is in the s0 and s1 states, like we have declared that what will be the ns. So with that the procedure block for the ns is completed. We have to write a procedure block 3 now, right? So here one thing we have to clearly understand is where I have to keep the present state for sure, and whether like jk you will be including or removing, right? That we have two options, right? Including or not including based on what kind of operations you require, mule operation or mere operation, mule or mere operations you need. Based on that we will have to, now I will do with the more operation, so I will remove this one. So my output is only depending upon present state, so this case will not be there, this arrow mark I have to remove it. So when this condition that operations across this one is the based on that same thing, I will be writing the same thing here, same thing over here. When it is in the same case, present state if it is something, or present state is something else, what will be the output that I'm trying to declare it again, right? So here when it is in the s0 state, so what happening is begin. So what happening is like we have to declare what is the output. So q is equal to what and q bar equal to what? Q is equal to 1 tick b 0 and q bar equal to 1 tick b 1, right? And the same operations need to be performed it once again in the s1 condition also. So I remove this one, I'll be going with this case, right? So there again when it is in the s0 state means the flip flop it is in the s0 state, so for sure the flip flop is in s0 state for sure. If it is 0 state, if it is a 0 state, it has to generate a 0 and 1. If it is a 1 state, 1 and zeros. So here I have to write it 1 and 0. So now after I define a third block, C1 block also. C1 block is defined, C2 block is defined, and M1 is block is defined. So finally I have to use AND module. AND module. Now save. So the same name JK30 it will be saved. Right, I will go with the total. I want to see the total GUI, right? So you can see the total GUI like this. You can see the total GUI like this, and this is what where I write a program. It's like similar with Xilinx ISC, nothing new. And what I do is I will be going with the process, and I will do the start compilation. Means like I have any error or any syntax error across my Verilog program or not, we have to verify it. So here it is showing the indication that here also it will show the indication. is there any errors or not will be observed over here. So we can monitor that in the console window. Here we have so many errors, right? So 21, there should be oh, begin, we used begin but we didn't use end, sorry, end. So that is one error, and we'll do save again and we'll go with the start compilation once again. Still I have error, still I have three errors, right? Yes, I didn't use end case here. Yes, again I'll go with the start compilation once again. Yes, so here we need to get a 100% process done. Yes, done. So after compilation is done, we have to go with the tools and go with the netlist. And as we know, after implementation is done, we can see that RTL view across the Xilinx ISC design tool. So here also the RTL view will be visible as it is. Let us see that. So this is how we have RTL view, and over here what operation is performing if you give the double click. So previously we could see the truth table and boolean equation logic diagram. For that different implementations that we have done it, but the implementation now done with FSM. So once you give the double click, we can see the FSM across that. So we need not to do the simulation, and we need not to go with each and every case. JK flip flop, if you give the reset, if you give that 0 0 combination, 0 1 combination. So that kind of conventional simplification simulation is not required. And here where S0 to S1, S0 to S1, you can see that S0 to S1, when there is a J input is high, when there is a J input is high and the reset is not high, means no reset, right? You can see that state diagram also like this. So here you can see that when j is equal to high, this is j and this is j equal to high, k is anything, k you keep, you have a 0 or 1 anything, so don't bother about the k. So j is equal to high and no reset, then automatically it should go from the s0 to s1. So the same thing is represented over here, s0 to s1 it is going, s0 to s1 is going upon the condition j activated j inactivated reset. So that's what like the condition from the state diagram also, like that we have to verify all the states, and the state diagram as it is, that what we assumed at the beginning, you got the same state diagram for the JK flip flop what we assumed, if it is generated by the state by the tool also, then we not to do any verifications again. So this is the simple way of like verifying the functionality of any kind of complex specification. If that complex specification, if you see it any another one, like I'll be giving examples, like if you see this is the paper where this is the complex circuit, it's like a DDR STM controller. So what we do is the controller will be having a state diagram. So state diagram where it has like so many states, not two states, three states. If like a four states, we need to go with the assignment, we need to go with the assignment. If like I have two states, I have to go with this one. Three states also it can be possible with the two variables. Three states also okay, four states also okay. When we have with the five states, we have to go with the three bits. So like that now for this circuit 1 2 3 4 5 6 7 8 9 10 11. So 11 states are there in the sense what I do is, So here my parameter assignments for the states is I have to use like S0 and S1. Instead of that, I have to use the dedicated assignments and dedicated notations given for the each state: ideal state, preacher state, actual state, and refresh state. So like that I will be using all the states. Ideal state, ideal state should be noted give assign with a 0000, because like four variables are required to assign a symbol for any kind of state, because like there are around like 11 states are there. If it is more than 16 states are there, I have to go with the 5-bit variable. So like that we have to know how that assignment is done for that each state, and we have to declare all the states in the parameter, and we have to increase the size of the PS and NS. There are 4-bit, in the sense 3 down to 0 we have to do it. And like S0 and S1 where ideal, active state, refresh state, like that we have to add all of them. And S0 S1, instead of that we will be having multiple statements. Here also you will be having multiple statements. So it's a very easy way of like updating the same program. I will be right, you can copy the same program in the description. You can take this one, and link for these papers, multiple papers also given in the description. You can go through the papers and you can implement this kind of complex specification by using the procedure, using this following procedure. So not only that one, if the sequence directory is given, like we have four states, 0 0 0 1 1 0 1 1, that assignment can be done. This is what one more example: when you have a vending machine where you put a coins, so it will be accepting coin, that is the state it will go. And if the number of coins that you use it is more than that, it will go to the reject coins and select product. And like that, whatever like the specification we have, as per the specification, that state diagram will be represented in the paper. So that's what we have to implement on the dedicated tool which is given to you, the Quartus tool. And the Quartus tool installation procedure and downloading the tool from the source, everything will be provided in the description. You can work on the Quartus tool also.